Hello everyone, today I will be demonstrating the operation of a BJT common emitter amplifier using LT-Spice. So the goal of this circuit is to amplify a small AC input signal while maintaining a stable DC operating point. For this design, I'm using a realistic 2N3904 transistor model and standard resistor values, including a 1.2k ohm collector resistor. So I will walk through 3 stages of the simulation to prove that the circuit works. So let's start with the DC analysis. So firstly, we go to configure analysis and we go to the DC out point. And then we run it. So as you can see in the results window, my simulated collector current ICQ is about 4.88 mA. To find my collector emitter voltage, I subtract the emitter voltage of 6.14 from the collector voltage of 0.48 volts, which gives us a DCEQ of 5.65 volts. This is an excellent Q point because it sits near the middle of our 12V load line, ensuring that our AC signal will have plenty of room to swing up and down without hitting saturation or cutoff. Next, let's perform the AC analysis. We go to the configure analysis and to the AC analysis tab. Type of switch decade, number of points per decade 100. Start frequency we put 1 Hz and the stop frequency we put 1 MHz. And then we run it. And then next, we click on the V out. So as you can see at the mid-band region, the circuit provides a maximum simulated gain of 15.27 decibels, which translates mathematically to a voltage gain of 5.8. Next, to find our low cutoff frequency, I drop the magnitude by 3 decibels to roughly around 12.27. And as you can see, the cursor shows this happened at exactly 1.217 kHz. Below this frequency, the input and output coupling capacitors react strongly and block the signal, which causes the sharp drop-off you see on the left. Finally, we look at the transient analysis. Configure the analysis again, this time with the transient tab. The stop time we put 0.2 milliseconds. And then we run it. Next, we need the V in and the V out of the circuit. So as you can see, the green trace is our raw input signal, peaking at around 10 millivolts, whereas the blue trace is our amplified output signal. Notice that these smooth rounded peaks proves that there is zero clipping distortion. Also, you can clearly see the 180-degree phase inversion of a common emitter amplifier. When the input signal goes positive, the output goes negative. Dividing the V out to the V in, we get a real-time time domain gain of 5.89. To conclude, I compared these simulation results against my manual theoretical hand calculations. So as you can see, these are the percentage error between the AC versus the theoretical and the transient versus the theoretical. We got 2.84% for the voltage gain and 4.26% for the low cutoff frequency, while for the transient, we got 4.43% error for the voltage gain. These minor variations are expected as the software utilizes a complex 2N3904 transistor model that accounts for real-world junction capacitance and non-ideal parameters that basic equations omit. Overall, the circuit operates perfectly and meets all design criteria. Thank you.